Welcome. So in this video we learn all about the auto-oxidation of fats. So especially we will focus on the auto-oxidation of milk fat. So auto-oxidation of the fats and oils is the topic of this video. Now first let me define auto-oxidation. Auto-oxidation basic definition is that auto-oxidation is defined as the oxidative deterioration of unsaturated fatty acid via autocatalytic pathway consisting of free radical chain mechanism. So this is the definition. Basic definition of auto-oxidation then is this, that it defines the oxidative deterioration of unsaturated fatty, because unsaturated fatty acids are involved, and it is defined as the oxidative deterioration via autocatalytic pathway consisting of free radical chain mechanism. So there happens formation of free radicals which give rise to the several reactions. So free radicals will result in the propagation of the reaction, and that we'll see subsequently. So actually this is the basic definition, that also oxidation is defined as the oxidative deterioration of unsaturated fatty acid, because unsaturated fatty acids are involved during the auto-oxidation via autocatalytic pathway consisting of free radical chain mechanism, and then the chain of reactions that happen during the propagation step that we'll see. Now, auto-oxidation is a autocatalyzed free radical chain reaction which is normally divided into three phases. So first is the initiation, second is propagation, and third is termination. Now coming to initiation, in initiation step what happens is that we have a unsaturated fatty acid. Say this is unsaturated fatty acid and this is a methylene group which is adjacent to this double bond. So what happens is then a hydrogen atom is abstracted from this hydrogen atom. So from this methylene group is adjacent to the double bond. So this methylene group is adjacent to the double bond. So a hydrogen atom will be abstracted, will be removed from the methylene group which is adjacent to the double bond during the initiation reaction. So it will be look like this. So CH double bond CH. Here you will have the CH, and the free radical formation has happened, and then one hydrogen atom has been released, that is abstracted. So there is formation of free radical. The free radical formation starts in the initiation reaction, and here it is in the unsaturated fatty acid, that is the methylene group which is adjacent to the double bond in the unsaturated fatty acid get converted to free radical, and this reaction is catalyzed by metals. So copper, iron, cobalt, nickel. So these are the catalysts. So this reaction is generally catalyzed by metals, may be catalyzed by UV light also, and also by singlet oxygen. So one is singlet oxygen and this triplet oxygen. So singlet oxygen is more energetic, and about it we will see in the coming slide. The singlet oxygen is having the one paired electron, that is unpaired electron in both the orbitals, in the outermost orbitals, that we will see in the coming slide. So the basic thing is that it is more energetic as compared to the triplet oxygen. So it can catalyze this reaction wherein a hydrogen atom is removed from the methylene group which is adjacent to the double bond. Now what happens during propagation step is that the free radical formation which has taken place. So this is free radical, it combines with the triplet oxygen. So here this is triplet oxygen to form the peroxide radical. So here we can see that triplet oxygen is involved in the propagation step, whereas your singlet oxygen is involved in the initiation step. So there is formation of peroxide radical. Okay, now this peroxide radical, what it will do, it will abstract another hydrogen atom, that is from the nearby fatty acid, unsaturated fatty acid. It will abstract the hydrogen atom, the way here it is been extracted, and then there is formation of hydroperoxide, and then again a free radical formation will take place, and this free radical will further abstract the hydrogen atom from the nearby fatty acid, and thus we will have a chain reaction that will occur. So several thousand reactions will take place during the propagation step until there is formation of stable products during the termination process or by decomposition. Okay, so this is a propagation step in which the free radical that has been formed, it reacts with that triplet oxygen to form the peroxide radical, and this peroxide radical abstract hydrogen atom from nearby fatty acid, and then there is formation of hydroperoxide, and then free radical formation is performed several thousand reactions, and these primary oxidation, this is peroxide, this is peroxide, and this is hydroperoxide. So peroxide and hydroperoxides are called as the primary oxidation products. So these are called as the primary oxidation products because they are generated during the start of the reaction, and they are primary oxidation, so they are flavorless, odorless. And then since these hydroperoxide and peroxide are unstable, they get decomposed to secondary oxidation process, which includes aldehydes, ketones, alcohols, volatile acids. These are the secondary oxidation products. And then in the final, the third step of the autooxidation is termination, where the free radical formation has taken place. They will be converted to the stable products. For example, this product will give you RR, this will give you ROR, this will give you ROR plus O2, that is oxygen will release. So all these are the stable products that has been taken place. These stable products may be aldehydes, maybe ketones, maybe volatile acids, or you have alcohols also. Sometimes alcohols formation also take place. Okay, so autooxidation, now the basic concept is that it is oxidative deterioration of the unsaturated fatty acid via autocatalytic pathway consisting of free radical chain mechanism, and that it is divided into 3 steps. First is initiation, second is propagation, and termination. And termination, there is formation of the stable products. Stable end product formation will be there, and then secondary oxidation products take place. And again told you that there are primary oxidation products and the secondary oxidation products. Okay, now the main cause of deterioration of lipids and lipid containing food stuff is the lipid oxidation or autooxidation. You need to say that autooxidation can be of 3 types. We will see that one is oxidative, one is oxidative autooxidation, oxidative rancidity. Second is we have oxidative rancidity there. Of course, this autooxidation is one factor that can cause the rancidity, and rancidity can be of 3 types. One is oxidative, other is ketonic, and third is hydrolytic. So among all the 3 type of rancidity is the oxidative rancidity, which the major rancidity that take place in foods. So among these 3 types of rancidity, there are 3 types of oxidative, ketonic, and hydrolytic. Among the 3 types of rancidity is the oxidative rancidity, which majorly occur in foods. And the main cause of deterioration of lipids and lipid containing food is also the autooxidation. That is, the oxidative rancidity is the major cause of deterioration of lipids and lipid containing food stuff. So on exposure to environmental factors such as air, light, temperature, oxidation reactions start to produce undesirable flavors, rancid odors, discoloration, and other forms of spoilage. So that we have seen that during oxidation, at the end, that there is formation of secondary oxidation products which are producing the undesirable flavors, rancid odors, discolorize the product, and also the sometimes result in the spoilage. Ultimately, the spoilage of the product take place. So majority of the changes are initiated by the oxygen reactive species, are leading to the formation of hydrogen peroxide. These are products, so alcohols and carbonyl compounds, these are secondary products, and carboxylic acid further oxidized products. So these we have seen already that these products for primary and secondary products, oxidation products are produced during the course of the autooxidation. Now, autooxidative changes implicate not only fatty acids but also the minor compounds such as vitamins and sterols. So not only fatty acids are affected, but vitamins and some sterols are not spared. They also get oxidized. Now, lipid oxidation can adversely affect the nutrition value. It affects the nutrition value, sensory quality, and shelf life of the foods. So these are the consequences of autooxidation that we will again see in the coming slide. That what are the major consequences of the autooxidation? Mainly, it results in the loss of nutritive value, because unsaturated fatty acid and essential fatty acids are lost during the autooxidation, and sensory quality, obviously, because there is production of flavors and others, that is due to the formation of the secondary oxidation products, and obviously then it will affect the shelf life of foods. Now, some products from the decomposition of hydroperoxide are potentially toxic also at a low concentration. Some of the products are also being toxic. That has been confirmed in the in vivo study, that the product of autooxidation some products are really potentially toxic at lower concentration. So under certain condition, a limited degree of lipid oxidation is sometimes desirable, especially in case of aged cheese and some fried food. So limited degree of lipid oxidation is desirable in in case of some cheeses, some cases like during some fried food, and also in aged cheese, like you have cottage cheese. It is desirable because there is occurs formation of methyl ketones during the autoxidation product, so it is desirable in some of the cheeses. Okay, now let us see what are the consequences of lipid oxidation. So first is nutritional consequences. There occurs destruction of essential fatty acids. There occurs destruction of fat soluble vitamins A, D, K. There occurs decrease in the caloric content because of course if fat is, because if fat is getting oxidized, then obviously the caloric content of the product will reduced. Okay, so there happens destruction. Nutritional destruction is there, that is affect the nutritional quality of the product. And then organoleptic, obviously when it other compounds or the compounds which are producing O flavors and others, these are being produced, then obviously then the organoleptic quality of the product will get affected. There are also occurs changes in the color, so it affects the competitiveness, reduce the shelf life of food products, and consequently decreases the sales. So these are the consequences of lipid oxidation. So major question till now is that what is autooxidation, what are its steps, and what are the consequences of lipid oxidation. So it affects the nutrition quality, it affects the organoleptic quality, and then ultimately affecting the shelf life of the food products. So there occur destruction of essential fatty acid, destruction of fat soluble vitamins A, D, K, and also decrease in the caloric content. And now if you see the organoleptic consequences, there occur development of rancidity, producing O flavors and others, and also there occur changes in color. So it affects the competitiveness, reduce the shelf life of food products, and consequently decreasing the sales. Okay, and now let us see three terms. There are three terms which are generally related with the chemical degradation of oils and fat. So first term is autooxidation. So it is defined as the oxidation of fat or oil at relatively low temperature, such as below 100 degrees Celsius. Okay, so autooxidation definition we have already seen, but here the simple definition is there, like oxidation of fat or oil at relatively lower temperature, such as below 100 degrees. That means to say that autooxidation happened at a lower temperature. Then another definition is thermal polymerization. So see that they have, please note that there is no oxidation which is mentioned over here. So we say that the change is taking place in oils or fats between 200 and 300 degrees Celsius in the absence of air. So first is that there is no oxygen is there, that is so that's why we are writing change is taking place in oils and fats between 200 and 300 degrees Celsius in the absence of air. And these type of reactions are mainly useful in the paints industry. And then the third definition is thermal oxidation. As the name indicates, it is happening at a very high temperature. So oxidation taking place at about 200 degrees Celsius in the presence of oxygen, because oxidation is there, so oxygen will come. And thermal is there, so at a temperature at about 200 degrees Celsius. So you must know the differences between these three terms. The oxidation happens at a lower temperature. Thermal polymerization, that is changes occurring in oils and fats between 200 and 300 degrees Celsius in the absence of air. And then thermal oxidation, that is the oxidation taking place about 200 degrees Celsius in the presence of oxygen. So these three terms you must know. Okay, now let us see about the oxidation of fatty acids which are present in milk fat. So what all possible compounds can be formed during the autooxidation of fatty acids? Some of the unsaturated fatty acids which are present in milk fat, that we will know now. So if you see that there are major unsaturated fatty acid, if you see, then one is C18 delta 9, that this means that double bond is at 9th position starting from the carboxyl group. So numbering will start from the carboxyl group, so at 9th position we will have double bond. This indicates that. And then this is oleic acid. Okay, now another C18, if we write C18 2 delta 9 12, this is linoleic acid. C18 3 delta 9 12 15 with the linoleic acid. C18 4 delta, this is if you see that here start from 5 8 11 and 14, this is arachidonic acid. Now there is a way, so we will discussing about the possible compounds that can be that are produced as a result of autoxidation of these fatty acids, these unsaturated fatty acids. So this is linolenic acid. This can be alpha linolenic acid also. This is the alpha linolenic acid, and if you want to draw for that is gamma linolenic acid, that is 6, 9 and 12. So this is gamma linolenic acid. Okay, so now we will see what are the possible compounds that are formed during the autoxidation of these unsaturated fatty acids which are present in the milk fat. Okay, so oleic acid is having 2 methylene group, give rise to 4 isomeric hydroperoxides. So what it means to say is that in oleic acid we have 2 methylene group which are attacked. So if you see that I have told you that during autoxidation what happens is that during the initiation step the hydrogen atom will be removed from the methylene group that is adjacent to the double bond. So if you see that this is this is a double bond at 9th position, in nearby it is CS2, this one methylene group is there, and here it is the second methylene group. So point of attack can be this also, can be this also. Later on we will see that this can give rise to this is actually 8, 9, 10 and 11. So the 8 can give rise to 8 and 10, and 9 can give rise to 9 and 11. That we'll see in the coming slide. But just to tell you, since in oleic acid we have 2 methylene groups which are attacked, so yeah, we will have 4 possible isomeric hydroperoxide. This line will be more clear in the coming slide. And in case of poly in non-conjugated system, so what is the difference between conjugated and non-conjugated? Conjugated double bonds and non-conjugated double bonds. Okay, so conjugated double bonds means that this is a double bond, this is CS2, this is another double bond. Okay, now we see that when there is double bond, then one methyl group is in between, and then it is coming the double bond. So these are not alternative, non-alternate, non-conjugated and non-alternate double bond. Whereas in the case of conjugated bond, if you see that CH double bond CH, CH again double bond CH. Okay, so this we say that alternate double bonds is there, one double bond, then a single bond, and then double bond. So these two are called as the conjugated double bonds. And later on we will see that non-conjugated fatty acid, these are non-conjugated fatty acids, more prone to autoxidation as compared to the conjugated fatty acid, that we will see in the coming slide. So in case of poly non-conjugated system, methylene group located between the double bonds are preferential. So this is non-conjugated system. So in this case it's the methylene group which is in between these two double bonds. This is the point of attack, this is the meaning. So this we will see in the coming slide also. Now in case of linoleic acid and linolenic acid, there are 3 and 6 isomeric hydroperoxides are possible, that we will see in the coming slide. Very simple how it's there once you know the mechanism. So mechanism of autoxidation of these fatty acid we will discuss in the coming slide. Mechanism of autoxidation of fatty acid we will see in the coming slide. Okay, now let us see first is the oleic acid. Oleic acid is having one double bond position at 9th position. Then we have linolenic acid which is having a 2 double bond which is position at 9 and 12 double bonds. And then we have alpha linolenic acid which is having 3 double bonds, that is position at 9, 12 and 15. And we have gamma linolenic acid which again is having 18 carbon atoms, 3 double bonds, position at 6, 9, 12. And then we have arachidonic acid C24, position at 5, 8, 11, 14. This I have told you in the previous slide also. Now let us see what is the mechanism of autoxidation of oleic acid. What are possible compounds can be formed by the autoxidation of oleic acid, that we will see. Now this is the structure of the oleic structure that we can see. So as told you, during initiation step the methylene group which is adjacent to this double bond will get attacked. So here 8 to 8 this will also attacked, or this will be attacked. So this star is not there because if when this star free radical is there, then one hydrogen atom has to be removed. So please don't incorporate here this star. Just this is just indicating that the position of attack or position of removal of hydrogen atom is adjacent to the double bond, that methylene group which is adjacent to the double bond. So either this point number 8 methylene group will be attacked, or 11 number methylene group will be attacked, and this reaction will be catalyzed by metals, that copper, iron or cobalt, and the UV light or singlet oxygen. So here we can see that. So if this 8 is the point of attack, we see that here 8 is the point of attack. By resonance it will give rise to 10 free radical also. So by resonance, so here we can see that the double bond is here. So by resonance, because free radical is there here, so double bond will get shifted to here, and then 10 number free radical will also form. If the point of attack is 11, say point of attack is 11, here we can see that point of attack is 11, then what will happen, it here it will give rise to, okay, so this is actually in continuation of this. So this will by resonance will form this, and then here it is shown that this is continuation 11, we will see later on. So here we have seen that at 8 and 10 position free radical formation has taken place. Now by the action of triplet oxygen, that we have seen that triplet oxygen, there is formation of peroxide radicals. So these are peroxy radical. So this full structure is not drawn, just to show that the peroxy radical has taken place, and then this free radical formation has taken place, and this free radical will abstract another hydrogen atom. That is, this free radical will abstract another hydrogen atom which is nearby to its fatty acid, and will get converted to hydroperoxides. So these are the hydroperoxides. So double OH group has come, so these are the hydroperoxides. Okay, now since these hydroperoxides are unstable compounds, so they get cleaved, they get decomposed to aldehydes. That what aldehyde will be formed, so the bond will break from here. So here one CHO, that is OH group, will be released from here, that is water molecule will get released, and then you will have the unduct 2 enal. So unduct, so CHO here, and then unduct 2 enal, because there is 11 number carbon atoms will be there in the structure. So unduct 2 enal formation will take place here if the position of attack is 8, and if the free radical formation is at 10, then bond will break from here, and we will have the N non-enal, because 9 carbon atom, and then this is aldehyde, so N non-enal formation will be take place. So these are the two possible aldehydes which can form from the autoxidation of folic acid. And then if the point of attack is 11, here I was telling you that if the point of attack is 11, so now this is not applicable here, so this, please ignore this. So this is not applicable. Say if the point of attack is 11, then it can give rise to 11 free radical, and also it can give rise to the 9 free radical also. Okay, now if the 11 is the 11 methylene carbon atom is the point of attack, then here what will happen is that first there will be by attack of the triplet oxygen, there is formation of peroxide, as it happens here also. The peroxide radical formation will be there, and then it will again abstract the hydrogen atom from the nearby unsaturated fatty acid or nearby alkylic acid, and then we will have the hydroperoxide. So if the point of attack is 11, then it will give rise to an octanol, as we can see here that an octanol formation will be there, because cleavage bond will be here. And if the points of attack is 9, then bond formation will be, that is the compound formation will be DAC2 enal. Okay, so by this way you can see that if we have the any unsaturated fatty acid is given to you, we can predict the compounds which are possible during the autooxidation of it. So here first we have to see how many hydroperoxide formation has taken place. 4, as there was the line in the previous slide that there are 4 hydroperoxide possible during the autooxidation of the oleic acid. Why? Because there is a single double bond, and then point of attack will be nearest to the double bond. It can be either 9 or 11, and 8 or 11, and then 8 will give rise to 10, and 11 will give rise to 9 by resonance, and then we can be able to predict that what are possible compound formation will take place. For example, here we have seen that N non-enal formation is there, and DAC2 enal formation is there, and then octanol and DAC2 enal formation is there. Okay. Now coming to autooxidation of the linoleic acid. Linoleic is having 2 double bond, that is at 9th position. So if we start 1, 6, 7, 8, at 9th position we have the double bond, and this is 10, this is 11, this is 12. At 12 position we have the double bond. Okay, now the point of attack will be this methylene group. This is in between the these two double bonds. So if a compound is having two double bond, then point of attack will be the methylene group which is in between the double bonds. So this will be the point of attack. Okay, so what happens, that point of attack will be at 11, and then by various metals, by various catalysts, that hydrogen atom will be abstracted as shown in the slide. So this is abstracted. So whenever free radical is written, then one hydrogen atom is always to be removed. So you cannot write here as free radical because hydrogen atom is attached here. Okay, so be careful when you are writing the structure. Okay, now this 11 can give rise to 9 free radical, and this 11 can also give rise to 13 free radical. Okay, then again the way we have told, triplet oxygen will come, peroxide radical will formation will be there, and hydroperoxide will be formed, and then the cleavage will happen from this side, and then we have formation of DAC2,4 dienal. DAC2,4 dienal, very simple. Okay, now if the point of attack is 11, then again there will peroxide radical will be there, abstraction of hydrogen atom will happen, hydroperoxide will take place, and then degradation will happen, and then there is formation of octuenal. So octuenal formation will be there, and the lastly, that if 13 is the point of attack, then again peroxide radical will be there, abstraction of hydrogen atom will be hydroperoxide will form, and then the cleavage will happen from here, and then you will formation of annexanal will be there. So during autooxidation of linoleic acid, there are 3 hydroperoxides which are possible, or we can say that there are 3 compounds, 3 aldehydes formation is possible. One is DAC2,4 dienal, after 2 enal, and then hexanal. Okay, now coming to alpha linoleic acid. Alpha linoleic acid having a structure is that 18,3, and then position double bond is at 9, double bond is at 12, double bond is at 15. This is the structure, very simple to write. Now again, as I told, that if the 2 or more than 2 double bonds are there, then the point of attack will be the methylene group between the double bonds. So here point of attack, this will be either 11 or it may be 14, because these two are in between the double bonds. So at 11 or at 14. So if at 11 will be there, then it will give rise to 9 and 11. So 9 9 and 13, it will give rise to, if the point of attack is 11, then by resonance it will give rise to 9 and 13. So again 9, there will be triplet oxygen attack, peroxide radical will be there, abstraction of hydrogen atom will happen, hydrogen peroxide will formation will be there, and then the cleavage will be from this side, and the formation of the compound DAC2,4,7 triene. Okay, now here if the point of attack is 11, then the compound formation, because the everything will happen in the same way, and the cleavage will be from here, this point, this will get broken, and then we will have OC2,5 dienal. Okay, now if the point of attack is 13, obviously that 13 is there, so peroxide radical, and then there is hydroperoxide, and then there is formation of hexenal. And this you can see, and you, when you are writing it in exams, or you have to write the full structure. Be careful that you have to write the whole structure here. Okay, now if the point of attack, as I told you, that if it's 14, then it will give rise to 12 and 16. So by resonance it will give rise to 12 and 16, and by all the reactions as told, that there is attack of triplet oxygen, then the abstraction of hydrogen atom, hydroperoxide formation will take place, and then 14 will give rise to pentuenal. Here this bond will get broken, and then 16 will give rise to 16. So this bond will be greater, 16 simple will give rise to n-propanol, and 12 bond, if the bond number 12 is broken, and then here this bond will get cleaved, and then you will have the HAP2,4 dienal formation take place. So there are 6 possible compounds which can be formed during the autooxidation of alpha linoleic acid. Okay, so these are the reactions which are occurring during the autooxidation of fatty acid which are present in milk fat, and we will able to predict the aldehyde formation, because these aldehydes are having indefinite flavor and odor, so this will contribute to the rancidity of the product. Then coming to gamma linolenic acid, gamma is having position at 6, 9, 12. So here if you can see this, at 6 position we have double bond, we have 9 position double bond, we have 12 position double bond, and then the point of attack will be here it will be, because the 2 double bonds are there, so in between the point of attack will be 8, or this point of attack will be this methylene group, or point of attack will be this 11 methylene group. So if 8 is the methylene group, then by resonance we have 6 free radical over the 10 number free radical, and then these 3 compound by all the mechanism which I have told you in the previous slide will result in the formation of tridac 247 trienal, undac 25 dienal, or non 3 enal, because 9 number of carbon atoms, undac means 11 number of carbon atoms, tridac means 13 number of carbon atoms. Okay, now here also if the point of attack is 11, then by resonance 9 free radical will also form, 13 free radical will also form, then you have peroxy radical formation, then hydrogen peroxide will form, and then because these are unstable they will get broken down into decompose into stable products like dep2,4 dienal, 2 dienal, and hexanal, and all these 4 are the compounds which can be produced during the autooxidation of the gamma linolenic acid. So this way we can predict the formation of possible compounds or possible aldehydes during the autooxidation of various unsaturated milk fatty acids which are present in the milk fat or ghee. Okay, so this is the mechanism of autooxidation. Okay, now let us see what all factors which are there which affect the rate of lipid oxidation in food. What are the factors which are affecting the autooxidation? So first is the fatty acid composition. So what type of fatty acids which are present in any food, that will dictate the speed of the autooxidation in the same. So it's the number, position, and geometry of the double bond which affect in the fatty acids, which affect the rate of autooxidation. Number, position, and geometry of the double bond in the fatty acids, which will affect the rate of autooxidation. So it's obvious that we have already seen that definition also, that it's the unsaturated fatty acid which are affected by the autooxidation. So in saturated fatty acid are less prone to autooxidation as compared to the unsaturated fatty acid, and then autooxidation of saturated fatty acid is extremely slow at room temperature. And if we compare that arachidonic acid, linolenic acid, linoleic acid, and oleic acid, the relative rate of oxidation is 40:20:10:1. That is mean to say that arachidonic acid, which is having 4 double bonds, that if you see, that is here C24 delta 5 8 11 14, is because there are 4 double bonds, is more prone to autooxidation 40 times. That is more susceptible to oxidation as compared to the oleic acid. So linolenic acid is 20 times more susceptible to oxidation as compared to the oleic acid. So linolenic acid, I've told you, C18-3 delta, it may be gamma or alpha. So if it is alpha 9 12 15 alpha, then we have linolenic acid C18-2, because there are 2 double bonds, so delta 9 12. Oleic acid, we have how many double bonds? For single double bonds. So this is C, then the carbon of atom is 18, and that is 1, and the delta is 9. So there is only 1 double bond in 9 position. So if you see the relative rate of oxidation for arachidonic acid, linolenic acid, linoleic acid, oleic acid, these are in the ratio 40:20:10:1. So this is the meaning of number of double bonds. More is the number of double bonds, more is the susceptibility of any fatty acid towards the oxidation. Then coming to position. So position, I have told you that non-conjugated bonds are more prone to oxidation as compared to the conjugated double bond. So non-conjugated means non-alternate double bonds, and conjugated means alternate double bonds. So if this is double bond here and here, so this is alternate double bonds, so this is less susceptible as compared to the non-conjugated. Non-conjugated means, so in between there will be methylene group interruption will be there. So if interruption is there in the double bond, then this is non-conjugated double bond, and this non-conjugated double bond first get converted to the conjugated double bond during the autooxidation, that's as we have already seen. So non-conjugated double bond are are more prone to the oxidation as compared to the conjugated double bond, as conjugated double bonds are formed during the autooxidation process from the non-conjugated double bond itself. Now if we see that 6 acids are more oxidate more readily as compared to the trans fatty acids. Now trans fatty acids are having you know that if they say this is a double bond, and if some different group is there, say what do you mean by cis and trans? If this is here some atom is there x, here also it x, and that is y. This is cis double bond, and then if the x here it changes to y, that is a c double bond, and this is x, and this is y, and this is y, and then this is x, then this is called as the trans fatty acid. So trans fatty acid, as we know that hydrogenated fat vanaspati is having is less prone to the oxidation as compared to the cis fatty acids. Okay, so because if the trans fatty acids are more in any product, then obviously that oxidation will be had, because trans fatty acids are generally that they are solid at room temperature, that is they stack stack like this. So if this is a trans fatty acid, so they can stack like this, they can form grouping, and this very difficult to oxidize them. Also they are very difficult to melt them. So melting temperature of trans fatty acid is higher as compared to the cis fatty acid, because there is a stacking of the fatty acid which takes place. But in case of cis fatty acid, there happens the kink formation will be there, and then stacking won't be possible, and since the stacking won't be possible, then these will be having the lower melting point, and also less are more prone to the auto-oxidation, and more prone to the oxidative spoilage. Okay, so this is the meaning. So number, position, and geometry of the double bond in the fatty acid will also affect the rate of oxidation that we have seen. Now the second factor is free fatty acids. So you know fatty acid, you always see this structure, you know that if this is CH2O, so this is a triglyceride molecule, and these are the fatty acid which is attached to the triglyceride molecule, and when these were acted upon by lipase, we will have the corresponding for fatty acid will be there, like R1, R2, and R3 fatty acids are there. These are free fatty acid, that is why these are free. And then where fatty acids means the acids which are attached to the triglyceride molecule, these are fatty acid, and when these are released from the, they become free from the triglyceride, these are another free fatty acid. So these free fatty acids are more prone to oxidation as compared to the as compared to the fatty acid which when they are attached to the triglyceride molecule. This is the point here. Now randomization of the fatty acid, say R1 I can change here, R2 can come here, R3 can go here. So likewise this is called the randomization of the fatty acid in triglyceride. It reduces the susceptibility to oxidation. So if you are randomizing the fatty acid in triglyceride molecule, it reduces the susceptibility to oxidation. Then large amount of free acids can facilitate in incorporation of catalytic trace metals. So if large free fatty acids are there, this can facilitate incorporation of the trace metal, and which are acting as catalyst from the equipment or storage tank, and thereby increase the rate of lipid oxidation. So if anyhow because fatty acids can also facilitate the incorporation of trace metal which are acting as catalyst, during the initiation stage of the auto-oxidation, thereby increasing the speed of the reaction. And how they do initiate the speed of the reaction, by lowering down the activation energy of the auto-oxidation. So you know that minimum energy which is required for carrying out the any reaction is activation energy. So metals will lower down the activation energy, they act as pro-oxidants, and if they are facilitating the trace metal incorporation, then obviously the rate of auto-oxidation will increase. Then coming to the oxygen concentration, so it's written when the oxygen is abundant, rate of oxidation is independent of the oxygen concentration. So if oxygen is saturated, oxygen is abundant, then your auto-oxidants won't be affected by the concentration of oxygen. But if lower concentration of oxygen is there, obviously oxidation is directly proportional to the concentration of oxygen, because both the singlet oxygen and triplet oxygen are involved, and during the auto-oxidation. So at lower concentration, oxidation is directly proportional to the concentration of oxygen. Now effect of oxygen concentration on rate is also influenced by other factors. So temperature and surface area again will affect the oxygen concentration. Yeah, because more surface area will be there, then more oxygen availability will be there, more increase in the oxidation obviously but there, and then the pressure is there, then partial pressure of the oxygen will increase, then also the it will affect the auto-oxidation reaction. Then coming to temperature, now obviously the rate of oxidation increases with increase in temperature, and Q2 value for auto-oxidation is observed to be 2. Means that if you are increasing the 10 degrees Celsius increase in the temperature, that will increase the rate of reaction by 2. That will double the rate of reaction. So if you are increasing the temperature by 10 degrees Celsius for any sample, then auto-oxidation will become double. That is the meaning of Q10 value. Q10 value is, if you want to define Q10 value, that it defines the change in the rate of auto-oxidation, a change in the rate of any reaction to with 10 degrees Celsius increase in the temperature. So if here it is getting double, so Q10 value is 2. Then temperature also influence the relationship between rate and oxygen partial pressure, that I will already told that partial pressure will increase, and then also that also will increase the auto-oxidation process. Now coming to surface area, now it is generally preferred that tall containers to be used. So if tall containers are there, less area of the sample or the oil will be exposed to the air, and then less auto-oxidation will be there. But if there are broad containers, then obviously the surface will that is exposed to the surface of the area of the sample that is exposed to the air will be higher, and this will result in more auto-oxidation. So rate of oxidation increasing in direct proportional to the surface area of the lipid exposed to the air, and tall containers are desirable for storage, as there is less surface area of the oil that is exposed to air, so less oxidation will be there. Then coming to the moisture, moisture at water activity of about 0.1, oxidation proceed very rapidly. So if we do the graph between water activity and auto-oxidation, so graph is only like this. Sorry, this is graph will be like it will like this. Okay, so here if this is water activity of 0.3, here it is water activity of 0.1, and here it is more than 0.13. so at water activity of 0.1, oxidation proceed very rapidly. Here it is proceed very rapidly because there is availability of the oxidants is there, and then increasing the water activity to 0.3. If you are increasing to 0.3, then it will retard the lipid oxidation of one producing a minimum rate monolayer, because here at water activity 3, monolayer formation of the water happens that prevents the access of the pro-oxidants to the fat, and thereby decreasing the auto-oxidation. But if the concentration is higher, then what will happen? Then the mobility of the pro-oxidants will increase, and then that will again further then increase the auto-oxidation. Okay, so this is the graph between the water activity and auto-oxidation. So here it is water activity, and here it is auto-oxidation. Okay, again repeating at point 1 that there is excess of water to the fat, and then there is excess of the pro-oxidants also. But as the water activity increases, then there formation monolayer formation that will prevent the access of pro-oxidants to the fat, and then thereby decreasing the oxidation. At higher concentration, mobility of the pro-oxidants increasing, again increasing the accessibility of the fat to the pro-oxidation, thereby increasing the auto-oxidation. So the graph will look like this. Now coming to potential pro-oxidants. So if we tell you that pro-oxidants are the compounds, these are the agents which bring about the auto-oxidation. Agents which bring about the auto-oxidation. So I've told you that some of the pro-oxidants are the first is the singlet oxygen and the triplet oxygen. So here singlet and triplet. So I've told you that singlet oxygen is generally involved in the initiation reaction, and triplet reaction only involved in the your propagation step. And the difference between that, this is triplet oxygen, that is singlet oxygen is more energetic one, and this is less energetic. Okay, so triplet oxygen is in the ground state, and this is an excited state. As the name indicates that we have these are the orbital, then both the lone pair will be there in the single orbital. Here one will be in the one each will be in different. So in triplet oxygen we have unpaired electrons, whereas in singlet oxygen we have paired electrons in a orbital. Okay, so these are just some of the difference, but oxygen obviously, because oxygen is involved, so it is acting as pro-oxidant, that is the agent which bring about the autooxidation. Then second is the riboflavin in light. This we have already covered, that riboflavin, you know that riboflavin in the presence of light get converted to excited riboflavin, and this oxidized riboflavin will convert the triplet oxygen to singlet oxygen, and this oxidation, again this will cause the autooxidation, and this singlet oxygen bring about the oxidation of some of the amino acids like methionine and converting it to methanol, which is giving it to the sunlight flavor, which is giving it to the sunlight flavor. Okay, now then next is metals, copper and iron. I have told you that metals are acting as pro-oxidant. They are putting down the activation energy and thereby is increasing the speed of the autooxidation. Okay, some of the metals like copper, iron, nickel, cobalt are the pro-oxidants which are there. Then coming to the metalloproteins, some of the proteins which have metal in them, they are also acting as autooxidation because they are supplying the mineral. Okay, then some metalloenzymes are there in the, like xanthine oxidase, they contain cobalt is there, iron is there, lactoperoxidase, catalase, cytochrome. So all these enzymes and these contain metals, and these provide which are again, you know, that are the catalyst and thereby increasing the autooxidation. Then one is ascorbic acid and thiols are also acting as pro-oxidants. So ascorbic acid is in milk is present at the concentration of 20 milligram per liter, and then is acting as an antioxidant at that concentration, and if higher concentration there, it becomes pro-oxidant. That is, it causes the autooxidation, that is speeds up the autooxidation of the milk fat. So these are the some of the pro-oxidants which are also affecting the rate of the lipid oxidation in food. Then the last is antioxidants. So this is the opposite of the pro-oxidants, that these are the agents which prevent the autooxidation. Okay. And then antioxidant can be primary and secondary, and primary is also known as type 1 and secondary also known as type 2, and these can also be natural and the synthetic one. Okay, so now what are primary antioxidants? So primary antioxidants are those antioxidants that donate hydrogen atom to the free radical formed during the initiation stage. So they say this free radical is formed during the initiation stage. This is antioxidant AH. So this will donate its hydrogen atom to free radical, forming a stable compound, and then free radical of the antioxidant will be generated. And similarly, if the peroxide value is this is peroxide, a peroxide radical will be there, then again there will be stable hydroperoxide will be there, and then antioxidant radical will be generated. And these antioxidant radical will form the stable products. These antioxidant free radical unable to continue the chain reaction, they won't continue the reaction and form stable products. As on the free radical of antioxidant combined to here it will give form the stable products. Similarly here stable products, here also stable products. So ultimately they are forming the stable products, will decay and form stable products by dimerization. So this is dimerization is there, or by reaction with another radical. So here they have reacted with another radical. These are the primary oxidants. They themselves are participating in lowering down the effect of the free radicals. They are themselves participating, they are themselves giving the hydrogen atom to the free radical, thereby terminating the reaction, thereby forming the stable products, thereby stopping the propagation step of the reaction. Now what are secondary stimulators? So what are secondary antioxidants? So secondary antioxidants are those antioxidants which themselves do not participate, that themselves do not convert free radical to the stable products, but inhibit the autooxidation reaction by numerous other ways. So numerous other ways, these four numerous other ways I have written. So again repeating, that secondary antioxidants are those antioxidants which they themselves not participate in the reaction, that is they themselves are not donating the hydrogen atom to the free radical, but are stopping the reaction by numerous other ways. That is the four ways or so. They can be metal chelator, so they will bind to the metals and thereby preventing the access of oxidants to the fat. thereby reducing the autoxidation. And metal examples are EDTA, citric acid, succinic acid, malic acid. These are metatherators. Then oxygen scavengers are there. Then they can be ascorbic acid or ascorbic palmitate. The oxygen scavenger means they are binding the oxygen towards themselves. Obviously, if oxygen is not available, then oxidation won't happen. Then some are singlet oxygen scavengers are also there. What they are doing, they are depleting the energy of the singlet oxygen and releasing it in the form of heat. Example are carotenoids. Carotenoids example is lycopene and the carotene. So these antioxidants, they are depleting the energy of singlet oxygen and converting it into heat. Then there are synergist also. Synergistic means if two or more than two antioxidants are used synergistically. Synergistically means 1 plus 1 is greater than 2, or 1 plus 1 we can say that there are 11. That means to say that if two antioxidants are used, then the effect will be higher as compared to the individual antioxidants. Say if we have a BHA, we have BHT, butylene hydroxyanisole, BHT, butylated hydroxytoluene, TBHQ. So these are the synthetic antioxidants are there. So generally these three are used in combination. So what will happen that if they are individually, some have an antioxidant activity, they are having some antioxidant activity individually, but when they are added in combination, then they will show the antioxidant which will be far higher than their individual contribution. Okay, so this is the meaning of synergism. Synergism means 1 plus 1 greater than 2, or 1 plus 1 equal to 11. Okay, now what happens is that, say we are using BHA and BHT, what will happen that first BHA will get converted to free radical, and then this BHT will provide hydrogen atom to this free radical, and then it will form the free it will regenerate the primary antioxidants. So synergistic and antioxidant, they regenerate the primary antioxidants and themselves forms the stable product. So this will form by a stable product by dimerization or by reaction with another radical, they will form the stable product. So these are synergistic. So this is the difference between type 1 and type 2 antioxidants. Type 1 antioxidants are those which are themselves participating in the reaction. They themselves will donate the hydrogen atom to the free radical, thereby terminating the reaction. And secondary antioxidants are those antioxidants which they themselves are not providing the hydrogen to the free radical, but catalyze but prevent the autooxidation by numerous other ways. They can be metal chelator, they can be oxygen scavengers, they can be singlet oxygen scavengers, they can be synergist. Okay, so now if you see some of the natural antioxidants, this tocopherol is natural antioxidants. Then here it's like a natural and synthetic. Natural antioxidants which are occurs in nature, and synthetic which are made chemically in the lab. These are the synthetic antioxidants. Example of natural antioxidants, all your vitamins like A, D, E, K. They can be they are occurring naturally in nature also. A, D, E, K, all these are the natural antioxidants. Synthetic, if you see that tocopherol is milk proteins are there. There are also some of acting as antioxidants. Carotenoids is there, ascorbate and thiols, malodipronine products, and then the antioxidant enzymes are there. Superoxide dismutase causing the dismutation of the superoxide, and sulfhydryl oxidase causing the oxidation of the sulfhydryl group. So all these are the antioxidants. And antioxidants, synthetic antioxidants are those antioxidants which are made chemically in the lab. Examples are BHA like butylated hydroxyanisole, butylated hydroxytoluene, tertiary butyl hydroxyquinone, TBHQ. Okay, these are the synthetic antioxidants, and the trend is towards the use of natural antioxidants because synthetic antioxidants are teratogenic, carcinogenic, mutagenic. Teratogenic means causing defective birth. Carcinogenic means causing cancer, or mutagenic means causing the mutation. So these secondary these synthetic antioxidants have been reported to have reported to have teratogenicity, that means defective childbirth, and then carcinogenic, that they're causing cancer, and then mutagenic, that is causing the mutation. Okay, so now trend is toward these natural antioxidants. Okay, so these are the factors which affect the autooxidation. So what we have covered in this video, we have learned about what is autooxidation, what are the steps which are involved in the autooxidation, what are the consequences of the autooxidation which are there, and then we have seen that what are possible compounds or aldehydes which can form during the autooxidation of various unsaturated fatty acids which are present in milk fat, and that mechanism we have seen, reactions we have seen, and then finally we have seen what are the factors which affect the autooxidation in oils and fats. Okay, so with this we have covered everything about the autooxidation, and in the next video we will cover how to determine the extent of oxidation. What are the various tests which are there which can help in predicting the shelf life of the oils, and also the degree of rancidity which has taken place in the oils, that we will see in the coming video. Thank you.